played by violin. So the semantic structure is that the music must have classical and violin property. We must make sure that the formed queries they have the same semantic structure so that human can understand the query. And the third property is that the distribution between different kinds of queries must be similar to the potential user queries. Once we have all the three properties, we can very safely use the formed queries to train the system so that the system will work well against unseen user queries. Okay? That makes sense. Because they have the similar property. This is the social query space we constructed from the online social data. The space is a hierarchy of music semantic concepts. So from the root music, we constructed 4 music dimensions: mood, instrument, genre, and vocalist. Within each dimension, we will have some clusters to group similar music concepts. For example, the mood dimension, we group into 4 clusters: sad, pleasure, angry, and joy. So within each cluster, we will have many more concepts similar to the main concept. But we can see that clearly. For example, joy. To joy, we have similar concepts: playful, yeah, something like that. For those small words that I can't recognize. The basic idea is clear. So once we have this social query space, we can easily form a meaningful user query by selecting or sampling those concepts and put them together. For example, I can select joy from the mood dimension and select classical from the genre dimension and form a user query, which is a music with joy and classical style. Right? That's good. That's how we form user queries. And this table lists the contributions of the online sources in constructing the social query space. The first one is that we use the tag base from Last.fm, MySpace, and Wikipedia. And from Google, we check some spelling errors. And from Wikipedia and WordNet, we will have some semantic relations. For example, homonym and synonym and hyponym. Hyponym is the relation describe the scope of the semantic concept. So, for example, if a concept has a larger scope of another concept, it's a hyponym of that concept. For example, animal and dog. Yeah, animal is a hyponym of dog. So, using all these online resources, we can automatically construct the social query space and form a large number of social queries. So this way, later on we will see, in this way, we will train a system with much better performance, generalization performance. Okay, so now we know how do we construct social query space from online resource and sample queries. So next, we will see how do we use the sample queries to train a regression model so that this model can map unseen user queries to their fusion weights to fuse the multiple fusion leads, to complete the search cycle. Here is some notations. Okay, in this model, in this page, we define a regression model. Regression model, we go back to the previous page. The input of the regression model is a user query. Output are some weights. So in here, we define the weights as a weight vector. It contains n weights. So if we have n underlying search experts, each expert has their own weights. And of course, the summation of all the weights equals to 1, and the range is between 0 and 1. The query-dependent fusion module, whether it's classification-based or regression-based, its goal is to derive the optimal weight W vector for each query cube here. So if you modify a model domain regression case, it's just a regression function. And according to the literature, we can decompose this so-called multiple regression model into some single regression models. Multiple regression model means the output of the regression function is a vector, it's not a value. We can decompose it into a series of single regression models with value output. In this paper, due to the popularity of support vector regression, in this paper we utilize it to realize a single regression model. So in this support vector machine setup, we use the X as to represent the query and YI represent a single weight. So that given to learn such a regression model, we will give a training set of query and weight pairs as the step, and then optimize this objective function of support vector machine. This is some details. You don't need to pay too much attention to that. Just know we use a support vector regression model to learn mapping between the query and the weights. Here is the actual learning algorithm we propose. I won't go through the algorithm, but the property of this algorithm is to achieve that the more training data we have, the faster the algorithm can train a support vector machine with the same generalization performance. A second property of this algorithm that is an online regression algorithm. This part is offline. It takes a set of training data and train a regression model. And it has another online part. Online part takes any single training pair, which in the real application, which will be the online user's query and each derived weight. So the algorithm can adapt itself, can adapt the regression model even by using an online user information. So that's the purpose of this design algorithm. So it's efficiency in learning and it's online adaptiveness. Yeah. Okay, basically that's the two main ideas we propose. To construct a social query space so that we can form a large number of social queries in training a better generalized system. The second part of the contribution is that we design a learning algorithm to train a regression model so that later in the evaluation you will see this model of regression has a much better property than the previous class-based query-dependent fusion approaches. In terms of evaluation, we used real-life data from YouTube. We crawled 17,000 music items from YouTube. Actually, the metadata is from Last.fm and the audio is from YouTube. So we did some human annotation for mood, vocalness, and instrument. For genre dimension, we used the ground truth from Last.fm. Because on Last.fm, user give each music their own tags. So we selected the most popular